Okay, so we talked in a previous conversation about how acids and bases donate, or rather make H plus ions in solution or make hydroxide ions in solution. Specifically, those were Arrhenius acids and bases. So now we're going to look at another kind of base, acid and base, pretty much the same thing, but there's some slight similarities, and this is going to be the most common definition of acids and bases that we deal with. So let's look at it. Okay, so we're going to be talking now about Bronsted-Lowry acids and bases. Bronsted-Lowry acids and bases. According to Bronsted-Lowry theory, an acid is a substance that donates H pluses, which is exactly what we showed in Arrhenius acids, right? But Arrhenius bases were different than Bronsted-Lowry bases in that they accept H pluses instead of, in Arrhenius, remember, it was making OH hydroxide ions in solution. Okay, so a Bronsted-Lowry base accepts an H plus in solution. So here's an example. Sorry for the background noise. The weather's so pretty today. I can't bear to shut my window. There's a little bit of cost that goes along with it, though. All right, so let's look at this. A HCl, which is the same example used for Arrhenius acids last time, it donates an H plus if it goes into water. This is supposed to be a plus sign right here. If it goes into water, because this H plus right here goes and piggybacks on top of the water molecule. Can you see that? So the water molecule goes from being water to hydronium. Okay? And so can you see how the HCl is an H plus donor and H2O is the H plus acceptor in this case, right? So in this case, this is acting as a base, and this is acting as an acid. So our learning goal for this section is to identify conjugate acid-base pairs for Bronsted-Lowry acids and bases. And haven't defined conjugate acid and bases yet. We're about to do that. So, an example of a Bronsted-Lowry base, we just saw an acid, right? A base is a good example of a Bronsted-Lowry base is ammonia, because ammonia accepts H pluses in solution, right? So here's ammonia. And if you put it in water, it takes an H plus from water. And if water loses one of those H pluses, what's left behind? Hydroxide, right? So you can see, by the way, that ammonia actually acts as both a Bronsted-Lowry base in this case and an Arrhenius base because it produces OH in solution, right? So in the reaction of ammonia and water, ammonia acts as the base that accepts the H plus, and water acts as the acid in this case that donates the H plus. Okay? All right, so let's do a learning check now. In each of the following equations, identify the Bronsted-Lowry acid and base in the reactants. Okay, so here's the reactants, and your goal is to identify which is a Bronsted-Lowry acid and which is a base. Okay, so pause the video, come up with a guess for that, and come back and check your answers against mine. Okay, let me suppose you paused it. Can you see that, first of all, this is nitric acid, and it has an H plus over here, or rather nitrate, it's got an H plus on it, right? And over here it's missing, so it looks like this is what donated the H plus. And it looks like it donated it to the water molecule, right? So this is the Bronsted-Lowry acid. And this, because it accepts the H plus, is the Bronsted-Lowry base, okay? And also notice there's a leading hydrogen here, which is oftentimes makes it real easy to see what the acid's going to be, right? So in this case, HF is an acid because it's hydrofluoric acid, right? We learned how to name that in our last section. Hydrofluoric acid, so it's the Bronsted-Lowry acid. Can you see how it's, after it gets rid of its H plus, it becomes F minus, right? And so that's the Bronsted-Lowry acid. And this then, in that case, is going to be the Bronsted-Lowry base. All right. Now, let's talk about the term conjugate. Conjugate acid-base pairs. In any acid-base reaction, there are two conjugate acid-base pairs. Each pair is related by the loss and gain of an H plus. One pair occurs in the forward direction, one pair occurs in the reverse direction. For example, if you have an acid here, which I'm just going to say generally is HA, once it gets rid of its H plus, right? So you see how once it gets rid of its H plus, it becomes A minus. So this is the acid, and this is the base. Okay? And can you see that when we're going in the opposite direction, this has an extra H plus on it, right? And so this is the acid, and this is the conjugate base in the reverse direction. Okay? So here's how we're going to do this. We're going to think about these things simply as going one way or the other, right? Look at this. Okay? So HF, for example, is going to become F minus after it gets rid of its H plus. I know it's a lot of language there, right? But H plus gain comes this way, and H plus loss goes that way. So if this is an acid, this is its conjugate base. If this is a base, this is its conjugate acid. Okay, and I don't think I want to say anything else about that. Another nice little picture from your textbook, but it's simply just showing the same thing a couple different ways. All right, so let's do a learning check. Write the conjugate base of each of the following acids. So here's how I'm going to do this. Realize I'm not giving you a chance to do it. I'm going to take off the H plus first, and I'm going to see what's left. After I take an H plus off, what's left? Same thing here. Take off an H plus. What's left after that, right? Can you see that if I take an H plus off here, Br minus is what's left? And it'll look like SH minus is what's left here if I take off an H plus. Can you see that? And if I take off an H plus down here, what is left? Probably should have given you a chance to try this on your own before I gave you the answers, right? It's going to be HCO3 minus. Okay, do you see that? Now write the conjugate acid of each of the following bases. And so what we're going to do in this case is we're going to say, well, if I add a proton to it, because a base accepts a proton, right? What's it going to be? Pause the video here and make a guess for each of these. Or not a guess, right? Make your educated guess. Okay, I'm going to suppose you pause the video, and NO2 minus is nitrite. That plus an H plus is going to give me nitrous acid. Right? Can you see that? And ammonia plus an H plus is going to give me ammonium. Right? And hydroxide plus H plus is going to give me water. All right, so let's close this conversation out with a learning check. Identify the acid-base pairs in the following reaction. Pause the video and make an answer for these and see if it's the same as mine. Okay, I'm going to suppose you pause the video, and I'm going to come here and say, all right, I see a leading hydrogen here. Looks like that is, this NO3 minus is what's going to be donating, right? So this is donating an H plus. Okay, so there's my acid, and there's my conjugate base. All right, so this must be the base, and sure enough, it looks like this is accepting an H plus, right? So this is going to be the conjugate acid. All right, so there's conjugate acids and bases for you. We'll get more chance to practice this in the upcoming sections. Good luck.